All right, so far we've been analyzing, asking the question, when I have a matrix equation, when and how, what can we say about solution? Why do I have solutions, and what can I say about them, and how can I go about calculating them? Well, let's take a little deeper dive. Let's say if I'm looking at the matrix A, whose entries are 1, 3, 4, 1, 2, 3, 1, 1, 2, 1, 1, 2. And my question here is, if I looked at this system with this coefficient matrix, can I always find a solution? And if I can, why? And if I can't, why? I want to know why. Can we actually solve for it? Well, if I want to figure this out, one thing that I can do is I can take it into a bit of an abstract perspective. Well, first off, note that our matrix, this linear operator, is operating on the third dimension and then sends vectors into the fourth dimension. So we're transforming third dimensional vectors into fourth dimensional vectors. And if I want to find an x such that when I take it from the third dimension and it converts into something into the fourth dimension, my vector b, it might contain entries such as b1, b2, b3, and b4. Okay, now x is going to be mapping it over into the fourth dimension, and if I want to solve, how do we always solve? At least so far. I can take the matrix, augment it with vector b, do some row operations, crank this baby out, put into RREF, and interpret the results. And I can do that if there's numbers or if there's variables. So let's do that. We'll have 1, 3, 4, 1, 2, 3, 1, 1, 2, 1, 1, 2. Augment B1, B2, B3. Doesn't that kind of mess with your mind a little bit? B4, shouldn't it be before B3, or is B4 come after B3? Okay, it's just weird things to think about. Like Optimus Prime, he's a transformer. Should he have life insurance or car insurance? I stay up late thinking about these things. I just don't know. Okay, anyways, let's put this into RREF. Look at that. That's amazing. It's the exact same thing. Someone's being nice. So take row 3, subtract it off row 4. 0, 0, 0, B4 minus B3. So what's the first thing that we can deduce here if this is going to have a solution? What can I say about the relationships between B3 and B4? Guys, they better be the same. Because if it's not the same, and you have something in the form of 0, 0, 0, and not 0, do I have a solution? No. My systems can be inconsistent. So to maintain consistency, I know automatically, I know right now that I can take vector B and I can recalibrate as B1, B2, B3, and B3. B4 has to equal B3. Otherwise, this is going to be inconsistent. Okay, now I just want to keep going along with the problem and see what else we can do. Maybe you can take row 1, you can pivot down, multiply it by -1. And also do the same thing down here. Let's do that. Because again, we said B3 has to equal B. Okay, well, if you take row 1, multiply it by -1, pivot down, you come up with this row. And also if you pivot down to this one, knocks out this entry, you're going to have -3 multiplied by negative, add down -2, and then you're going to have another -2 right there. And likewise, -1, -1. Now, to put it into RREF, I need to go a little further. I could maybe just multiply this by negative, switch the signs, And then maybe take row 2 and multiply it by 2. It's my choice. We can do it. Scale it by 2. And then take row 2, add it to row 3. Well, keep going through the process. Maybe take this row, multiply it by 3, and let's maybe pivot up. Okay, and as we keep doing this, what we're going to come up here in the very end after we simplify is we're going to come up with this matrix right here. And down below, again, these two things would have to be the same. So B3, B4 would be identical. I know it's going to look like this. Now, in order to maintain consistency, what can you say about that row? Could you have 0, 0, and not 0? Not if you want to be consistent. So for consistency, you need this to be 0. So B1 would have to equal 2 B2 plus B3. Now, I can come over here, I can update my vector yet again. I know what's going to happen here at B1. So I'll just take it and replace it. So in order for this system with this coefficient matrix to have a solution, the vectors, the output, they have to have this structure to it. If you don't have the structure to it, then it's not going to work. But what is it really about this vector B that's caused me to have solutions? So once again, why do I have solutions and what can I say about them? Okay, let's keep going further with this. Okay, so if you look at your vector B, one thing we can do is pull this thing apart. You'll have 2, you have 1, and then 0 and 0. B3 minus 1, 0, 1, 1. So in other words, B would have to be in the span of these two vectors. Well, that's interesting. It's got to be in the span, otherwise it's not a solution. And a span, again, is the set that contains not just 1 or 2, but it contains all linear combinations. And you can think of B2 and B3 as being parameters, you can do whatever you want it to be. So really, this is the whole entire solution set corresponds to this matrix. But go deeper. Why? This works, but what's going on with these vectors? 2, 0, 2, 1, 0, 0, negative 1, 0, 1, 1. Well, if you come over here and if you look at your matrix, and I can look at a matrix from a number of different perspectives. I can look at it maybe in terms of the columns, where I have column vector A1, column vector A2, column vector A3. And if I just pause for a second and just note what's happening here with vector 2, 1, 0, 0, I see that I can take this vector and I can reformat it. I can say A2 minus A1. And likewise, this vector, I can reformat this as 2A1 minus A2. Check it out. See if it works. Take 2 copies, extract off a copy. Do you get that vector? Yeah. If you take vector A2, extract off vector A1, you'll have 2, 1, and then 0, 0. 2, 1, 0, 0. Well, that's really, really interesting. And what if I was going to take this and reformat it just one more time? Because again, these are vectors. B2 and B3, those are constants. They're some kind of scalars. And I can take it and reformat it as 2B3 minus B2, vector A1 B2 minus B3, vector A2. And what did we show? We showed something absolutely amazing. Something that I should have seen earlier, but I didn't really see it yet, but now I'm seeing it. It says if you take vector B, which is going to be a solution for this matrix, vector B has to be a linear combination of the columns A1, A2, and I can also say A3. I can zero it out. But why did the vector A3, the coefficient, why did that zero out? Well, look at the columns again. If you take this column, you add it to this column, you get that column, the third column. And if a column or a vector, if it's in the span of the other vectors, what can you say about that relationship between the vectors? They're going to have to be linearly dependent. But with these two vectors, these vectors are going to be linearly independent. And I just need my linearly independent vectors to reform the whole entire solution space. Whoa, that's pretty cool. So all this time, we're chasing this question of solutions. What can I say about them, and when do I have them? It all boils down to one simple observation. As long as vector B can be expressed in terms of the columns of the matrix, then it's a solution. Well, with something that's groundbreaking, we probably need to have a special name for it, as opposed to saying, remember that thing we did on that day, that thingamajig? And probably saying the hippopotamus space. That'd be great to call it that. It just doesn't have all that nice descriptive elements that we're probably going to need. So a better name is to say column space. The column space of a matrix A. This is a vector space. Okay, this is a vector space. And we denote it as the column of A, and we can say span A1, A2, in this case, A3. Or I take the span of all of the columns. As long as B resides in the column space of the matrix, then AX equals B, you can solve this. So let me ask you the question then. We're encountering at times systems which are inconsistent. Why were they inconsistent? Because the vector B was not in the column space. So for consistency, you need this. And if vector B is not in the column space, you're going to have an inconsistent system. You can't solve it. It's not solvable. Well, that kind of begs up some other questions. If it's not solvable, what can we do to get the best case scenario? And we might need to do some kind of numerical approximation to figure out the best case scenario that's going to get close enough, whatever that entails. Every single vector space, irregardless of what space it is, there's going to be certain vectors which is going to allow you to reform the whole entire space. And those vectors, those are known as your basis vectors. Your basis vectors may be denoted as beta, and we'll say V1, V2, Vn. Let's say they're going to be a subset in the nth dimension. You could have m vectors or 2 vectors. That's okay. You just want to make sure you don't exceed the value for m. Because if you exceed the value for m, what's going to happen is you're going to destroy this aspect of being linearly independent. Because remember, if you have a matrix, and if you have more columns than you have rows, what can you say about the relationships between the vectors? Are they dependent or independent? They're going to be dependent. And in order to be a basis set of vectors, you need two things. The first thing is it needs to make sure that you can span that whole entire space. So the span of vector B for the basis vectors, and let's say it's for vector space B. And the other criteria is the basis set beta has to be linearly independent. If you don't have one of those, it's not going to be a basis for the space. Now, here's an interesting thing again. If you have a set of linearly independent vectors, the span of linearly independent vectors, that will always form some kind of subspace. It may not be the whole entire space, but it will form a subspace, like we saw in the last example, where we're looking at the column space of the matrix. Well, here's the next question then. If every vector space has a certain set of vectors you can use to reconstruct the whole entire space, how do you find them? How do you find basis vectors? Well, how am I going to find vectors which are linearly independent? Well, take your matrix, go through row operations, and identify the pivot columns. In other words, find the basic variables. So if I go back to the example, when I look at the RREF, and really you don't have to look at RREF, you just need some kind of echelon form to identify where the pivot columns are. RREF just goes a little bit further, gives more information you really need to answer this question. Look over here to see which are your pivot columns. Then trace it back to the matrix in question. You would select column 1, and then you would select column 2 because there is a pivot over here in the echelon form for column 1 and column 2. These vectors are going to be linearly independent vectors. Now, here's the deal. This is where a lot of students go sideways. Don't do this. Lots of times what's going to happen is a student's going to come up here and they're going to say, the column space of the matrix. I say, yeah, that's right, column space. Well, let's give me the span. Well, that's perfect. I'm loving this. And they're going to say it's going to correspond to this vector right here. And I say, oh, you're so close. These vectors do not construct the columns of matrix A. Just look at it. If you take any linear combination of this vector with that vector, would you ever get 0 right there? You'll never get 0, as much as you try. As much as you think you can identify, you're never going to get that value right there. It's just not going to work. So row operations disturb column space. But row operations, they won't distort or disturb something called row space. The row space of a matrix is also a vector space, and we can denote it as row A. This is going to be the span of all the row vectors. So you can call this maybe row 1, row 2, row 3, row 4 in this example. And if you add a row to another row, what do you get? You get another row. And remember, in order to be a subspace, to be a vector space, you got to have that aspect of closure. If you add something of the same entity to another same thing in that same space, you're not going to pop out of it and get something else. If I add a row to another row, I'm not going to generate a column. I'm going to have a row. And if I scale a row, am I going to take that row and pop it up like a transpose? No, I'm going to scale the row by the particular value. So this is definitely a vector space, and row operations will not influence the vector space if it's a row space. So if I want to identify basis vectors, and basis vectors are again vectors which are a spanning set, it's linearly independent, I could first off say all these vectors are in my row space, and that's true. But for a basis set, I want the smallest set, the minimum set. And I can just snag and grab those two. I do not want to come over here and grab those. Because what if the matrix originally, what if it was this? And I did a row operation to turn it into this. And then I did another row operation to turn it into that matrix. If I trace it back to the original matrix, would you say that those two vectors would comprise the whole entire row space? Are they basis vectors? Are they linearly independent? Not even close. They're dependent vectors. So to find the basis for the row space, look over here. If you want to find a basis for the column space, go back to the original matrix. I know you're probably not sure about this idea of basis quite yet. You kind of got it, but you don't kind of got it. So let me explain it to you in another way. You got your colored wheel. And in your color wheel, if you want to make the color purple, how do you make purple? You take a little blue, you take a little red, you mix them together, and as you mix them together, you create purple. And based upon how much of this you're going to use and how much of this, you're going to get a different shade of purple. So in other words, maybe take 50%, 50%, 70%, 30%. You're going to scale it in a way like that. Look what I did. Linear combination. Oh no. This is where I get in trouble. When I'm looking at the color wheel, it really is mathematical. If I want to make orange, I would do the same thing. Take certain colors. I don't have to take all the colors with me if I'm going to do some kind of painting. All I really need are three colors. The primary colors. I can't take the red and I can't take blue or yellow and write in terms of the other colors. Since I can't write those colors in terms of the other colors, what's that say about the primary colors? None of those colors can be re-expressed in terms of the linear combination of the other, so they're linearly independent. Whoa. And you can get every color under the rainbow using those three colors. It's going to span everything. It's a spanning set. So you have a basis set of, dare I say it, vectors for the colors. This is nothing more than linear algebra. Don't tell anyone. They get mad in the art department because I like to color by numbers. Okay. Okay, maybe I really do, but numbers. And was there something else? I can think of my color wheel, the green, the blue, the purple. I can think of it really in terms of vectors, because what if I was to recalibrate a vector in which I looked at the amount of blue it would need, the amount of red I would need, and let me say blue, red, yellow. I can take it, express it in terms of those standard basis vectors. Now that's getting too crazy here. And if I'm looking at a vector space, the dimension of a vector space corresponds to the number of basis vectors which will comprise the whole entire space. How many colors do I need to reconstruct any color that I can see? 3. What does it say about the color wheel? It is a vector space because you add a color to another color, you don't get a cat, you don't get a dog, you get another color. Now you can use those colors to the color of cat or dog if you want, but you're still getting another color. The colors we see is third dimensional. So you have a third dimension on top of the third dimension in terms of the colors, everything we're seeing here. That's really starting to blow your mind quite a bit. Because the colors, that does form a vector space. And everywhere I see the colors, maybe over here, it's a certain vector, it's being scaled. It just blows your mind when you start thinking about it. So, a basis is nothing more than a minimum set of basis vectors, or linearly independent vectors. It's got a span, and you want to have the minimum, so that's why it's going to be linearly independent. Now, again, you could take more colors with you. You can take blue, red, yellow, green, purple, orange, whatever. Take them all with you. And you could still construct all the vectors. It will still span, but it's not the minimum set of vectors you're going to need to go ahead and reconstruct everything. Okay, well that's pretty interesting. So every vector space will have a basis set of vectors, but it does not need to be unique. All you need are basis or linearly independent vectors. If you're in the third dimension, you need 3 basis vectors. Any 3 would work as long as they're linearly independent. The natural choices are things such as E1, E2, and E3. But you can also pick these vectors right here. Those vectors would also work, but also form a basis set for the third dimension, which is embedded in the fourth dimension, since we're talking about 4x1 vectors. Okay. You guys sure you really want to know about this thing called the matrix? Are you really sure? Because as we go deeper into the rabbit hole, you always got a choice. Red pill, blue pill? What choice would you make? What do you really want to know? Okay, so when you start taking things into different dimensions, weird things start happening for sure. But anyways, it's probably a good place right here to pause it here for today. We'll talk more about these topics next time. You guys have a great day, and I will see you next time.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.